Hello everybody, and welcome to the top of page 46 in the workbook. And in this video, we're going to basically just be summarizing some of the key properties of gradients. And in particular, we're going to do this as a comparison. We've already talked about gradients of functions of two input variables. We're going to contrast that behavior with a function of three input variables, just so that you can see side by side the similarity and differences between the two situations. Okay, so let's start with the first bullet point here under z equals f of xy. We already know that if you draw a graph of a function of two input variables, it lives in three-dimensional space, whereas the domain occurs in two dimensions because we're talking about just the two input variables. What would the analog of that be over for the function w equals g of x, y, z? Well, there we just basically have one dimension higher, so the graph would live in four-dimensional space, whereas the domain would be in three-dimensional space, okay, for the x, y, and the z. All right, and then we come to facts about the gradient vector, and let's start over in the left-hand column. Okay, so the gradient lives in two-dimensional space. Okay, if you take the gradient of a function of two variables, what do you think about the gradient of g then? Well, it should just have one dimension higher, so it's going to live in three-dimensional space. Okay, and then we jump back over to the left column again. We know that the gradient of a function of two variables points in the direction that causes the fastest increase in the value of z. Notice that z is the output, okay? And so over here, we could make a similar statement, but what's our output value in this case? It's going to be the w. Okay, so that's going to be the maximum increase in w, our output variable. Okay, back over to the left. And what about the magnitude of the gradient? Okay, well, we know that the magnitude of the gradient gives the magnitude of fastest increase in z. There's that output variable again. Okay, and so over here on the right, the magnitude of the gradient is just going to give the maximum increase in w because w, again, is our output variable. All right, so hopefully you're seeing there's kind of a nice parallel going on between these things. Okay, so continuing down the list here, for a function of two input variables, the gradient vector is orthogonal to the level curves of f. What would the analog over here for this function of three variables be? Okay, well, instead of level curves, we have level surfaces. So the gradient vector should be orthogonal to the level surfaces. And in fact, we saw this a little bit in the preliminary example that we did. We had a level surface that looked like a cylinder. We drew in a couple of gradient vectors and saw that they were orthogonal to that surface. Okay, and then finally, last point, if we have a unit vector, we've got this nice formula for calculating the directional derivative as being the dot product of our gradient times our unit vector. And the formula for function of three variables is exactly analogous. We're still going to take the gradient and dot it with our unit vector. Same formula, we've just got an extra term. Okay, and that's it for this list.